So let's just get into the topic. I was thinking a little bit about the title. So I wanted to have lessons learned somewhere in this title, and I wanted to have EuroQCI in this title. But, well, lessons learned through EuroQCI sounds a little bit weird because the EuroQCI actually haven't really started. So ways to quantum safe networking. So we've been active in the quantum type of project since a couple of years right now when it comes to the POC through trials and ending up with an actual commercial deployment. So I just wanted to get all of us on the same page. So what about this quantum topic? So what is a threat and how we can mitigate it and what's coming up next? So let's maybe just start with the basic principles, right? So everyone talking about a quantum threat. So where this quantum threat is actually sits. So as you all probably know, the ways to secure the data in motion is to do the encryption according to the standard AES-256, widely adopted, very robust. But in order to establish this secure communication, we need to have also a key exchange protocol. So, and there are mathematical models which are telling that the AES encryption, the symmetric AES encryption, it's going to be safe against the potential power of the quantum computers, but actually the attack surface is below. So in this key exchange process, so the asymmetric key exchange process, as we widely use today, the Diffie-Hellman, the models shows that could be actually cracked with dedicated specialized algorithms like the Shor algorithm, for instance, and with the potential power of the quantum computers. So you may say, well, why should I care, right? So the quantum computers sounds like a science fiction still, right? So they may be up, I don't know, in 5, 7, or 10 years from now. But actually the reason why we should care about it right now is actually about the harvesting data. So the malicious organizations today, they can intercept the data communication, even if it's encrypted right now, they can store it. And many years later, they could use quantum computers, once they're available, to crack into those data, breaking into the key exchange algorithm. So, and there are many organizations which cannot let that happen. So think of financial institutions, think of I don't know, medical data, governmental data, or military data. So that all of that kind of informations which couldn't be revealed even from 10 or 15 or 20 years from now. So that's why also the European Union and its organizations, they also recognize hey, we need to do something about it. And there was a program launch around it. It's called EuroQCI, and we really see this is a catalyst for accelerating the deployments, the research and innovation towards that direction. So all of the participating countries, they sign up the declaration and saying, all right, we wanted to build something which is quantum secure. We want it to be ready by 2027. We would like to have national secure links, but also the cross-border, and also there's going to be some space components associated with that through the satellite communication. So what are the goals, or the targets, or the strategy behind that one? So the master plan is to, first of all, to upgrade the existing infrastructure, to augment this with quantum resilient techniques in order to provide the secure services. And at the beginning, that's going to be for public institutions, governmental institutions, European institutions, just to secure the data transmission. But also what is very important these days in this deglobalization trend, as we're saying, to also stimulate the technology independence in Europe. So we are not dependent on American, on the Far East technology, so we have our own homemade technology which we can trust. And in a long-term vision, there is a master plan to provide some sort of a construct like the quantum internet, so the medium which we can all use as consumers, and which is going to be a quantum safe. So this is far and forward-looking goal, but it's on the roadmap. So right now, getting a little bit more into technical details. So that's the program, but how we can actually make the networks quantum secure. So, and here there are two main techniques or options which we are having in order to mitigate the risk which we're anticipating right now. So on the one hand side, there's something like a post-quantum cryptography. So actually the mathematical methods which are replacing, or actually the algorithms which are going to be more robust than the traditional Diffie-Hellman which we use today. So, and on the other hand side, there's quantum key distribution, so actually using the quantum physics in order to make the key exchange even more robust. So I'm going to talk a little bit more about those two options. So again, at the beginning, quantum key distribution. So what is a quantum key distribution? Again, it's going to be very in a nutshell because it's really complex process and there's really complex protocols behind it, and there is a couple of ways of doing so. We have a BB84, we have a CVQKD, DVQKD, and many other things. But in a similar fashion, like we don't have to, understand perfectly well how the car engine works, for instance, right? But we need to know that, well, if we're running out of gas, then the car stops, yeah? So in a similar fashion, trying to explain that one without going into the protocol specification, to achieve or to actually build a quantum key distribution, we need to have a quantum channel, so additional medium, and some sort of like a service channel. And there's going to be some portions of the information which are coded to the qubits. And the most important feature to be understood about the quantum communication is in case whomever is listening or trying to eavesdrop to this quantum channel, then the quantum state collapse. And therefore, the listener, so Bob on this picture, is recognizing that someone was trying to tap into, therefore, it's ultimately secure. Again, tapping into the quantum channel makes the information which is being carried over to collapse. Therefore, it's honestly impossible to eavesdrop in a very, very high simplification. So in a practical implementation, as we build it, right? So these days we have to have the regular transmission equipment, whether it be like WDM system or Ethernet systems or on the upper layer, and we need to have some additional layer as the quantum processing tools, and they are exchanging information through the quantum channel. They are processing that and distilling the quantum key, which is being fed to the transmission devices, and that then transmission devices can establish the secure transmission. So this is how it works in a principle. So among the others, we did such an exercise a couple of years ago in UK with BT, University of Cambridge, University of York, Toshiba, and ID Quantic to building the actual real-life communication using a quantum key distribution, so proving that this is actually possible. But thanks to that exercise, we really learned a lot. So again, in a key summary, so what I've learned, so what things to be remembered about a quantum key distribution. So the safety is really given by the quantum physics. Again, that it's impossible to eavesdrop, so it's super secure for sure. But on the other hand side, it requires additional channel. So you can actually, well, there are techniques to multiplex it into data transmission, but then we're reducing our reach. Even using a separate fiber, it's also, the reach is quite limited. Therefore, it might not fit into the existing infrastructure sometimes. So that gets into another point, yeah? So it's not like a very simple overlay, so you just overbuild the network. You have to consider your distance limitation of the QKD system. You have to consider how to build the trusted nodes and how to actually make to fit all of that together. Well, it might sound relatively simple in a short distance in a data center interconnect environments, but in a longer distance, regional infrastructure, trust me, it's a big challenge. So, and lastly, there is a lot of standardizations going on, right? So as I said, there is a multiple protocols which can be used, and there's no like final conclusion in the market industry. This is the way to go. So it's all in progress, and I guess we all are aware about that one. So then, quickly about the second option, so the post-quantum cryptography. So here's this, well, it might sound a little bit easier because it looks like we used to have the Diffie-Hellman or some other protocol, and right now our goal is just to replace it with a different algorithm, with different key exchange mechanism. And there are some standardizations effort going on by NIST, for instance, in US, or by BSI in Germany and many other organizations. And there are mathematical models. There are some candidates of the protocols which are being perceived as a quantum secure. So even with quantum computer power, even with a Shor algorithm, they are being considered or assumed as a quantum resilient. So that's basically the same principles of the encryption and the key exchange, but with a different algorithm. So we also did a similar exercise. So one of them we did, it was within the research and education community. So in that particular example, we've been connecting with WDM 100 gig signal from Trondheim up in Norway through Sweden, Denmark, Germany, down to Poland, to Poznan. So, and the takeaways. So first of all, okay, it's security is based on the principles which we know today, on the same mechanics, but we're just using a stronger algorithm. There's no distance limitation, so that's a great advantage. Over here, we don't need additional fiber, but on the other hand side, that requires, those new algorithms requires a lot of computing power, so a little bit more computing power hungry than the other ones. So that represents a little bit of the challenge, which has to be taken into consideration. And lastly, it's also work in progress. So they're shortlisted algorithms by NIST, for instance, but they haven't announced yet what is the final, and the really top robust algorithm. The candidate and the recommendation which we're seeing is a classical Mac-Alice. So again, just to sum it up, the quantum technologies, on the one hand side, they are creating a problem. So there will be a quantum computers with a really great power, and thanks to that, they will be able to crack into the existing key exchange algorithms. But on the other side, so we can actually, to mitigate that, we can apply post-quantum cryptography using a stronger algorithms. But also on the other hand side, the same technology is also providing a solution. Because of that quantum physics, we can actually make the communication even more robust and more secure, but we just need to overcome those challenges I talked about just previously. So all in all, speaking about those challenges, yeah, so we all here know how the networks look like. It's not just monolithic devices. There is a bunch of different vendors. It's not a green field. This is like low power embedded platforms with limited computing resources. While if we're talking to the industry saying, okay, so we'd like to apply and QKD and PQC, and we want it to be cheap and easy to integrate and cost-effective and simple. So yeah, it's still a heavy lifting to marry all of those points and requirements. So what is actually the current recommendation as we are tracking the standardization organizations? The recommendation is actually to apply both. None of those options is a silver bullet saying PQC is better or QKD is better. The better is both. So actually to make a combination within the transmission system, apply AES-256 encryption, and on top of the current Diffie-Hellman, put the PQC like a classical Mac-Alice, for instance, and give additional layer of the quantum key distributions, mix all of that together and create a secure, robust, quantum secure communication. And again, it's not only a program, it's not only research. I just try to collect a couple of comments or quotes of the big operators all over Europe, and actually every single of them, they're taking some action. So they're they're not only researching that, but actually figuring out, thinking how to deploy it commercially. And actually, just a couple of weeks ago, BT was announcing they made a commercial QKD installation in the city of London, and they have a first commercial customer who's the EY, actually. So those things are truly starting up, even though there's still a lot of question marks behind the technology. So summarize what's our role, actually. So we are technology vendor. We are doing boxes for a transmission. So, but over the, well, more than last decade, we've been focusing on the secure transmission on ADVA, also on the WDM, but also on the upper layer devices. So we introduced the AS-256 encryption in 2010, and since then we've been trying to continuously innovate. So therefore, when this technology or concern pop up about the quantum security, we also started up our own research towards that direction. We got engaged into multiple standardization organizations and try to launch and participate in many programs, also European programs, to try to address that one. And last couple of seconds, I just want to say, okay, who you are. I just already mentioned a little bit. So we are the vendor of the ADVA, the vendor of the communication systems, and our solutions are based on the technology tripod, as we like to say. So 3 main lines: optical transport, from access through metro core and the data center, Ethernet aggregation, demarcation, but also powered up by the network function virtualization, and a very special product family for sync and timing distribution over the networks. So that was it. Very brief from my side. Thank you so much.